All right, today it's gonna be a little bit math heavy, a little bit. But before that, let's just do some quick reminders, okay? Just about something you should really watch out. Not much. Your assignment number 1 is gonna be due, I believe, next Monday, but please check the precise deadline, okay, on the PDF. And doesn't need to be perfect work, but I will really suggest you guys try to struggle as much as you can about the different tasks. They will definitely help you on the subsequent programming test. And before the actual programming test, I will also release some example questions for you guys to practice. But one thing you can practice right away, the split array harder, right? I just made it available a couple of days ago. So that one there can also train your recursive thinking. So if you really get struggle with how to solve this extended version, drop by, reach out. I can give you some conceptual hints. But you can just follow the pattern that we spoke about the simpler version, a split array. It's very similar, but you do have to make some extra consideration, especially how you can manipulate the array list library classes. And guys, don't forget, in your assignment number 1 section, so there are some links about how you can use the array list and hash map. It is okay that your previous course doesn't cover that, but that's something you can pick up on your own. If you got any trouble understanding that, let me know. Question. Yeah, if you want to use you can use as many helper methods as you like. They don't need to be recursive even. Yeah, question? Array.clone? You know, I would suggest try to avoid library classes apart from like array list or hash map that you're required to use. In the actual programming test, which I'll be a little bit more precise, it will be forbidden to actually use library classes in general. So I would say try to practice. I think all the solution can be done without using any extra clone method, especially for clone. It's going to save you some work that you're going to do on your own. Okay? Yeah. Guys, any other questions? Yeah.
Are we allowed to use member variables as globals or no?
You mean like a static variable?
No, like a member variable as like a global you can write to between the recursive calls.
I would suggest if you want to have any variable that's going to be shared among the recursive call, it's better to really practice style just by passing the arguments in between. That might be the more style that you can kind of get used to. But if you want to use static variable, like a global one, not the most ideal way. Yeah.
Well, I was just going to say, it's just for the first one, so you avoid having to use substring constantly.
Yes, you mean the first task? You definitely want to avoid using substring. Yes, you definitely. I think if you can just use it from like the pattern we spoke about, that should be just enough. Yeah, good. All right. Anyway, so if you've got other questions, feel free to stop me after the class or during office hour. We can speak more. Okay. Yeah, my office hour you guys know pretty well, and also the TA contact information, right? All right, let's do a quick recap from last time. All right, so last time we actually spoke about different vocabulary. Let's now do a very quick mention about them, right? May not dive into the detailed definition, you guys can review. So given some computational problem, which should have some well-defined input and expected output, right? That's normally what we focus on. Given that you're going to have some algorithm, it could be more than one algorithm for which you want to compare and choose the better one, which we'll speak about more today. So given the algorithm, of course, from the user's point of view, it's going to be the input and expected output. And internally, the algorithm will have some steps manipulating the data structure you would choose, right? Once we finish the asymptotic analysis, we're going to dive into some more data structure, but we're going to build a foundation first. And once you got your algorithm, you're going to judge that by 2 criteria. Correctness is always the number 1. If you don't have correctness, don't even talk about efficiency, okay? And for correctness, we're going to focus more on the testing, which you're going to practice in the programming assignments and also programming test. And for efficiency, we got time and space. Both are important, but for this course, we're going to focus more on the time perspective. And we talk about how you can use experiments, building some table about running the elapsed time, visualize the result. All good, but they do have some limitations, which we spoke about last time, right? You can review the limitation. That's why we try to move to something more mathematical, what you learned in 1019. So today, also part of Thursday, we're going to do a little bit like a repetition from 1019. I just want to make sure everybody is kind of comfortable with the math that you're going to apply to analyzing algorithm. And then we'll see more example about applying the mathematical analysis to algorithm, maybe the second half on Thursday's class. But for today, more math. Okay. The time is something we got to focus on. All right, so that's the experiment problem that we spoke about. You can also review the details there. And we spoke about primitive operations for us to count. And one case will be accessing the attributes. We assume that it's always going to be constant operation, like always primitive. So the number of dots you might have is not going to depend on the input size, never. And then we got also a method call. I was trying to be a little bit vague at this point since we haven't seen many case studies about analyzing methods. But for you guys, purpose just for now. Just remember that in order to analyze the running time for a method call, you have to dive into the details about the method. So your conclusion could be the method call itself may be a primitive operation, maybe, or it may be a non-primitive operation, could be either. So you just have to do analysis. Now we're going to see more starting from Thursday, right? And also whenever we talk about new data structure, we always have to revisit, like what's the running time, always. All right, so that's the last example we did, which is about to count the precise number of primitive operations, right? So I may not repeat the details, but you guys got to remember, whenever you're given something that will involve a loop, it's always a good practice to at least talk about these two questions over here, about how many times the condition here is going to be evaluated, and also how many times the body of the loop is going to be executed. They're somehow related. Once you can figure out one number, the other one should be also quite straightforward, right? Always try to answer these two questions before you actually start analyzing the code. Not today, but on Thursday, we're going to see how we can handle more complicated cases. For example, what if you got a nested loop? How do you handle that, right? We're going to learn about how to observe the patterns on the loop counter. In that way, you got to be very careful about laying out the patterns, which I'll show to you next week, not next week, hopefully Thursday. All right, so before I move on, two things. So that's the last slide that we spoke about. So the final answer is 7m minus 2. All right. So this is a formal representation about how many primitive operations that will be involved in execution whenever you try to find max. As I said earlier, as n goes larger, maybe from 1 to 10, 10 to the 100, the resulting number here, you can just do the math, it will be larger and larger. Right? We said it's a linear growth about the running time. We'll see a little bit more about the growth of functions today. We'll definitely do. We got to make it more precise. All right, and then I'm going to leave this page clean over here on slide number 15. So this example here is very similar to the find max. I'll leave that to you guys for practice. Okay, I somehow haven't included the answer on the slide, only some hints. I will also include the solution, maybe a little bit later, just about at least the final answer you can check. All right, so I'm going to leave this to you. This one is going to be exercise. And some questions as hints are here. You can print this page out and also try it out. Right? This could be some, like a written test or exam question on the easy side. All right, but at least get the easy ones understood first, and then we'll do the more challenging one a little bit later. Okay. All right, any questions? All right, let's now move on. And I would like to start with a very important idea today, right at the front. Right? So we talk about basically running time, and we talk about how you can calculate the precise number of primitive operations. In some way, we are still talk about more like absolute running time. But today, we're going to talk about why we can safely move from absolute into relative. That's something I want to convince you. At least we want to walk through the process, which is very important. Straightforward idea, but it's very important. Okay. So what I will do is, let's go over some bullet points, and then I'll start from scratch on some clean page. Let's talk about the idea together. So here, we say that each primitive operation, by definition, they will take basically a very small amount of constant time for execution, depending on what the platform is, right? It could be Mac, could be Windows, depends, okay? So it really depends on the execution environments. So that's why we call them the absolute time. But this might turns out to be not essential for our analysis purpose. I'm going to show that to you. Okay? So I'm going to do something that's a little bit concrete, but also a little bit hypothetical. But hopefully that can carry out the idea to you. Okay? So this is a question we got to answer here, and then I'm going to build a solution from scratch. So the question goes like this. How do we relate the number of primitive operations that's required by some algorithm, for example, 7n minus 2, to the actual absolute running time, depending on what the execution environment it is? So that's a question we want to answer. All right, and let's now build this one from scratch. All right, quickly. So let's start with the very important variable in our equation, t, little t. So what is this? This one will be the exact time, or absolute. Time that's taken to execute a primitive operation in some execution environments. So that means the value of t may vary from one environment to another. Let's make some concrete example. All right? This may not be the newest model, but let's say Mac M1. Okay. Let's say on Mac M1 chip, t may just be, let's say, 2 milliseconds. Let's say. And another platform, let's say the current Mac I'm using is back in 2014, much older. That one presumably is going to take a little bit longer time for maybe the primitive operation. Let's say that, for example, that could be the Mac, but a different version. Maybe that's back in 2014. And that one there will be a little bit slower. So 4, taking more time. All right, as you can see, that's the variation we might have for t. And we want to somehow see the following problem. Let's say we got the same algorithm, we got the same computational problem, and we got 2 candidates or competing algorithms to really choose from. We want to see which one should be chosen. And remember, time efficiency will be our main criterion. So the less time it will take, then we should take that one, right? So I'm going to build a table just to show you. And then we're going to see why somehow this t might just end up being not essential for our analysis. We're going to make sure that one's convinced before we can drop it safely. Okay. So I'm going to draw some table here. Okay, so let's see here. Okay, that's the table. Okay, that should be big enough. Okay, so we got some header over here. I'll mention that. And we got 2 rows over here. And that. All right, and then over here, we talk about the number of primitive operation, right? So I'll just call that maybe more like an absolute running time. Okay? And then one algorithm could be, let's say, 7n minus 2. Like a find max. Let's say to solve the same problem, there's another algorithm, which will be 10n plus 3. So you can think about these two are the absolute running times of 2. You can say either competing or alternative algorithm, solving the same problem. Alternative algorithm. Presumably solving the same problem. All right, and then just for completeness, let me also annotate about the n over here. So the n over here and also the n over here, they simply denote input size. And for simplicity, let's assume n is simply 100. Okay. Let's assume for our discussion, n is simply 100. Right? So for example, you can simply plug in, right? 100 over here and also 100 over here. However, when you say 7 times 100 minus 2, the number there is not the time just yet, because you haven't really considered whether it's going to be executed on this platform here or this platform over here. We got to calculate that as well, right? So let's do that. So we got two possible execution platforms. Either we got the first one, let's say Mac M1. Also, we got Mac 2014, let's see. So what we're going to do is we're going to fill out 1, 2, 3, and 4. Each one of them is going to be the precise running time on that particular platform. All right, let's do that. And then I'm going to show you in two perspectives why T is not essential. Right? It's important to realize that too. All right, let's try this. Let's say for the same algorithm that will take 7n minus 2 primitive operation to execute. Let's say for this one here, we can either choose to execute it here or choose to execute it here. Right, let's try that first. So that one there is going to be, let's say 100, right? And here will be 100 times 7 minus 2, right? You can see just this formula here and plug it in by the assumed input size. And then we're gonna multiply that by 2 because we're talking about 2 Mac M1, right? And similarly, to execute the same algorithm on a different platform. So this part over here will just be the same. Agree? That's kind of the mathematical part that we derived last time. But it's just that executing each primitive operation will take different amount of time because it's different platform. So this one here is also going to be 100 times 7 minus 2, but now this will be times 4. All right? All right, so now just for comparing the same algorithm, it is not so essential to really consider this part over here. Because normally when you consider the same algorithm, you just want to know abstractly how many primitive operations it will be required to execute. Whether or not it's going to take maybe another 2 extra milliseconds in another platform for the same algorithm, it's not so useful for your analysis purpose. Right? So that's why these two can be dropped. All right. So these two, let me just highlight it. This one here, and also this one here. Okay, these two. So when considering the same algorithm, it is not necessary to know the precise running time difference. Again, the running time difference I'm talking about here is about 4 versus 2. It's not so meaningful, right? Because it's the same algorithm. So that means T can be disregarded. Disregarded. All right? All right, so that's about comparing the same algorithm on different platforms. Let's talk about another situation. Okay? Let's now also fill out this entry over here. That one there would be, I'm still trying to execute the algorithm on M1. Pretty efficient, presumably, or relatively more efficient than this, presumably. But now I'm going to consider a different algorithm. So that one there, I'm going to say, so here, 100 times 10, right? The 10 here corresponds to the 10 here, plus 3, and then multiply by 2. Right? You can see the 2 here and the 2 here just correspond to the 2 here, right, for that platform. And without having to fill out this entry here, you can do that if you are interested, but we can already make some conclusion here. If you look at these two cases, okay, I'm going to just make sure it's clear, stands out for you. Let's say these two over here. Let's think about what's the original purpose, what we're doing here for the analysis. We want to somehow to say, given these two representing the running time somehow, primitive operation required for 2 algorithms, we want to choose one that's actually more efficient. do we really need to consider the extra factor 2? If we drop it, that means we only consider this and this. That might just be sufficient. Why do you have to multiply the whole thing just by 2 at the same time, right? It can just be simplified at the same time, right? Agree? That's a very simple mathematical property. Whenever you're talking about compare two things, you can just divide them by the same amount. It will just give you still the same quantity to compare. All right, so this one here, also not essential. So this will be when comparing, not the same algorithm, but different algorithm. When comparing two different algorithm. Also not essential, not necessary. To consider the extra common factor. And the extra common factor I'm talking about is 2, because it's common to be multiplied to this and this. We can just drop it. All right. So far we talked about 2 scenarios. Scenario number 1, the same algorithm on different platforms. Scenario number 2, we talk about different algorithm on the same platform. In both cases, we can just disregard t. So the conclusion is we just don't need to consider the precise time for each execution platform in any analysis that we're going to do. Right? That's a conclusion. All right. It's a very important conclusion, straightforward again, but you really need to understand why we can make such transition from talking about milliseconds or nanoseconds to just about mathematical equation, right? You want to really know how we make that transition safely. All right, any question here? All right, I hope that's straightforward. All right, let's now move on to the slides. I think everything has been said over here. So the actual running time will just be proportional to the number of primitive operation, right? It should be some multiplication by the precise execution time, t, right? But we can drop it. All right, so everything else will just be the same as what I said. And this will be the final conclusion. Let's read it together. To determine the time efficiency for the algorithm, from now on, we are only going to focus on their number of primitive operations. And here, when I say the number of primitive operations, we learned about how to count them precisely. Right? Of course, you should know how to count them precisely. But we're also going to see in many cases, we might just need to approximate the number of primitive operations, which I'll show to you. Okay? For example, 7n minus 2, we might just approximate it as n only. But there's a rule that we got to follow. I'll get there. Okay. All right, this slide here, guys, is very important, right? Just to understand why we go from one to another. Okay. Okay, approximation. Okay, let's now talk about approximation. And I'll give you guys maybe some extra practices about counting the precise number of primitive operations, either when we are getting a little bit closer to the written test, or maybe a little bit, just a little bit later. I just need to find out where exactly I put them from previous year. All right, so let's now go over some bullet points. I will need to review some terms. You may have heard about them maybe in 1019, but it's good to brush up about the details over here, which we're going to use quite often throughout the course. I do have some a little bit more complicated example than this, but let's just go over the terms on the slide very quickly. And then I'll go over one example with you from scratch. Okay. All right. So let's say we got 7n minus 2. That's the find max primitive operation. And you can view that as, for example, here. Okay, hopefully everybody has no trouble, right? Just for what it's worth. N here is simply n to the power of 1. 2 here is 2 times 1, and 1 there is n to the power of 0. I'm pretty sure you know, right? And we say that if we got 2 polynomials over here, we got power of 1 and power of 0. And we know that the highest power here is the 1. The rest is so-called the lower terms, right? And also for 7 and 2 over here, besides the polynomial, we said that these are the multiplicative constants. Right? So these are the terms we have to make sure we understand how to identify them. We'll do one example just in a moment. So we got highest power, and also we got multiplicative constants. and also we got lower term. And just notice that in this case, we only got this one here is a single lower term, but you may get multiple lower terms depending on the example. Okay. And whenever you want to approximate a function, so here are some simple rules you can follow. Basically, you want to think about this. If I somehow want to observe how fast this particular function can grow, right? If you plot some graph, let's say you got the value of f of n, and also you got n in the horizontal axis, which we'll see some example. If you want to see how fast this particular graph is going to grow, it would be sufficient if you only try to monitor the dominating highest term, how it grows, right? That's really the insight into it, but we'll see, all right? So you only have to focus on the highest power. That's really what it matters, especially when we talk about asymptotic context, meaning that the input size gets very large. Okay. When the input size gets very large, this particular lower term does not really have much impact about your observation. So you only got to focus on the highest term. And also for multiplicative constant and also lower term, they can all be dropped. Okay. And you should really get the highest term left. Okay, so this one here, just you can think about this one here. You will only get n left. But let's do one example from scratch. And I want to just make sure everybody is comfortable with the terms. Okay, this one here. That's also on your slides. Okay, so we got 7n plus 2n log n and also 3n squared. Okay, apparently we got 1, 2, and 3, right? You can see 2 plus. So we got 3 terms over here. And somehow we want to approximate this particular function. And this function might just represent the number of primitive operations of some algorithm. Okay. Let's now take a look. Right? Let me copy that, and then I'll talk about some various details. There will be also some assumption we are making for the course. So this one here, 7n plus 2n log n plus 3n squared. All right. First of all, whenever you see log for this course, usually we will be quite explicit about the base, but just in case you see the base is missing, usually just 2. Right? Computer is more like a binary system. And also later on, when we talk about trees, the more exciting cases we're going to talk about will be binary tree. So there's also log base 2. Right? But of course, if I really want a different base, for example, 3, I'll put 3 explicitly here. Right? So if you don't see the base, 2. By default, base 2. All right, that's the first point to make. And then let's now rewrite this function here slightly, okay, by kind of considering more precisely about the power for each polynomial. All right, and then we got to decide, once we are being very explicit about the power or the exponent, so we can choose the highest power correctly. Okay, let's do that first. So let's say this one here, 7 times n to the power of 1. Right? I'm pretty sure you're okay with this. And plus 2 times n to the power of 1 times log n. Of course, if you want to put 2 here, that's also fine. Okay? And then plus 3 times n to the power of 2. Right? So this is what's given, and this is how you should think of it precisely. Of course, if you're so good in math, you might just be able to choose the right one anyway. But I'm just trying to show to you the process here. All right, so what power do we have? Somehow we got 1 here, we got 2 here, so these two are simple to identify. But now for this one here, seem to be somewhere in the middle, right? So we got to be careful about this one here. So n log n is something we're also going to run into quite often, especially if you talk about sorting algorithm. And if you got a sorting algorithm that's n log n, it will be considered as an efficient one. For example, merge sort and quick sort that we're going to see later in the course. Okay, so n log n is not an uncommon running time you'll run into. So you got to make sure you understand that. So what I would do is, let's talk about the power here. Apparently, you can see this. This is power 1. How about this one here? how about this power here? You're gonna kind of approximate, right? We're gonna see exactly where it is. So what I would do is let me isolate this term over here. Okay, log 2n. And this one here, though, in order to really get some intuitive sense about its about its exponent, so think about this. So this is roughly about n to the power of something, roughly. Okay, just getting some intuitive sense. In order to get that number there, you want to think about how fast the function is going to grow. Okay, it turns out this question mark over here is going to be somewhere between 0 and 1, somewhere. N to the power of 1, sorry, n to the power of 0 is going to be something, just 1, constant, right? And also n to the power of 1 is something just linear. And log is just going to be somewhere in between. The best way to illustrate this, well, let's not dive into too much about mathematical analysis. Let's see some diagram. So let's say this. I'll put it here. So draw some plot here. There's also another nicer plot later in the slides and also on the page. But let's now focus more on just the constant log and also linear. All right. So let's say we got the value of n over here, the horizontal axis, and also we got f of n. And we want to somehow compare these three. We want to compare n to the power of 0, which is constant, and also n to the power of 1, which is linear, and also log n. Right? We're going to consider these three. All right? Linear is easy, just like that. N. Linear. All right? 1 maps to 1, 2 maps to 2, 3 maps to 3. Right? Constant is also very straightforward. Constant here would be just like, for example, constant 1. Just like a flat line. All right? How about log? You don't need to draw precisely, but at least you should have the intuitive sense. Log is going to grow much slower than linear. Something like that. All right. So what you can think about is for log 2n, the rate of growth now is faster than constant, the n to the power 0, but slower than linear, n to the power of 1. All right? Hopefully you're okay with that. So you can think about the power here is 1 here. Okay, let me just go back here. Let me use different color. So the power here is 1. And the power over here is about 1 point something. Sorry, less than 1. Beg your pardon. Less than 1. All right? So you basically got the multiplication between something that's of power 1, something that's of power less than 1. If you combine them together, it's got to be 1 point something, right? Strictly less than 2, right? That's the conclusion. So if you look at the entire term, n log n over here, that one there is actually going to give you a power 1 point something. Right? The reason I'm talking about this is really for us to choose the highest power appropriately. So now we know that this term here, the power is 1. This whole term over here, the power is 1 point something. And this one is 2. Right? So that is highest power. So we should really choose that one. Okay. All right, let me now make that selection. So this one here, n square is the highest power. Highest power. And it is important to identify this because asymptotically, it is going to dominate all the other lower terms. I'll talk about asymptotic, more definition about it a little bit later. It basically means, asymptotically means towards the limits, towards infinity. Okay. Asymptotically, this highest term dominates over all the rest. Over the rest. All right, that's good. And let's very quickly identify other things. Okay, so if you look at, for example, let's say 7 here, 7 here, 2 here, and also 3 here. So these are the multiplicative constant. All right. And also here. So multiplicative constants. All right, final thing. Since this is the highest term, the rest will be lower term. Lower term number 1, lower term number 2. All right, very quickly. So think about this guy over here, and also this guy over here. Okay, these are the 2 lower terms. Yeah, many things, but they are all straightforward. But I think the main tricky thing here is to really see n log n would not be the highest power to identify, right? That's the main message here. Any questions so far? We're good? All right. All right, so I think, okay, make sure I don't miss anything. Oh, okay, I forgot the most important thing. So after all these, if you want to approximate this particular function, which is the original question, the answer should be n squared. And the way it works is like this. I'll just write down the answer first, and I'll do that. We'll do more exercises. Okay. So the approximation result will be just n squared. The way to do that is like this. I identify this to be the highest power. I drop the multiplicative constant for the highest term. Also, I drop all the lower terms, and I only got this left. Okay, that's the process. We'll see more example in a moment. Okay, drop the multiplicative constant and drop the lower term. You only got the highest term without any multiplicative constant. That's the approximation, the simplest one you can get into. And this is also very important for you to also get some intuition about big O. But for big O, having intuition is not enough. You also got to formally prove it, which we'll also speak about today. Okay, so that's good. So that's exactly what we just said. But all the details you can find back in the page. Okay, so let's now talk about more approximating. Okay, so we got running time function, number. Okay, that's good. Okay, so this slide here, it just gives you like a list of the common functions you should really be aware of about the rates of growth. Okay, I also got some diagram there to show to you. Just one moment. So we got constant, we got logarithmic, we got linear, we got quadratic, n to the power of 2, cubic, and also exponential, etc. So these are the common ones. But you might run into something maybe in between. For example, n log n that we just spoke about, right? So let's now take a look at some summary, quick. So this diagram is also on your slide. You can also take a look, but let me just highlight what you should, some of them, okay? First of all, let's see the constant here. Constant function will be the most ideal running time where you will want to get into for your algorithm. Because constant function simply means it doesn't really matter how large the input size is. You will always return, you will always require the same amount of primitive operation to execute. I'll get to there, right? So first of all, let's identify the constant, which will be right here at the bottom there. So this one grows the slowest. On the other hand, the one you want to avoid, in general, will be exponential. But of course, sometimes you may have no choice. Maybe that's the easiest way to really program, right? This will grow the fastest. And for that one, for exponential, let me just draw that quickly. It's exactly here. You can see as input size go large, it go exactly that, right? You can see even for small input size, it goes this big for running time. And whereas for the constant, it's still this low, right? All right, let's see something in between. Oh, before that, let me just talk about the constant, right? Just to give you some idea. So when we talk about running time, right? If I say f of n is simply equal to 1,000. Think about it, it's more like 1,000 times n to the power of 0, right? Whenever you got to the power of 0, that means a constant time function. You might be thinking 1,000 sounds pretty big, but it's not big anymore when the n gets very large, okay? So if you have an algorithm like this to say f of n, n will be the input size, let's say the array size. This one tells you if you got, let's say, an array of element with only one element there, it will require 1,000 expensive in this small scale. However, if you try to grow the input size, f of 1,000, if you got 1,000 element in the array, it still requires 1,000. If you got f of 1 million, you got 1 million element in the array, it still require 1,000, and etc. So that's really the value about constant running time. Especially when you see the very large input, you still got constant. That's why constant operation, the constant running time is something you will hope to get into. But it doesn't happen that often, all right? But at least you should know, theoretically. All right, very quickly. So let's say the linear that we just saw earlier, you can see that linear is exactly here, okay? I'm gonna put it in orange, this one here, this is linear. All right, this is linear, and the logarithmic that we spoke about is actually just in between the constant and also the, okay, let me draw a little bit better. Just in between the constant and the linear, right? You can see this is linear, this is constant, in between you got logarithmic, and etc. Right, just look at this diagram more closely just to see, right? To get some intuition about different running time functions. You really want to see how they grow. Okay. So after this, let's see. Okay. Yeah, so this slide here just to say about the different cases we might consider when we talk about running time. So let's just try to understand this graph over here. So you got running time, the vertical axis. For the horizontal axis, it's just about different test cases. Think about A is like a test case number 1 for particular input. And we got 1, 2, 3, 4, 5, 6, 7. 7 different test cases, right? So worst case time simply means choose the longest running time that can happen, worst case. And best case will be the shortest running time. Of course, for your analysis, you should really not try to just do best case running time, because in that way you might be underestimating how long your algorithm might take. Right? Worst case, which we're gonna focus on. The average case time here is interesting, right? This one here will be the most sophisticated one to really calculate. We don't talk about it too much in this course. There is one example there in somewhere in my slides. We'll see if we can get the time to really cover. But at least in the principle, whenever you talk about average, you're talking more about probability or average that you want to calculate. That one definitely requires heavier math to analyze. But we'll see if we get there. Otherwise, just remember the principle. But for this course, we only focus on worst case. We don't really want to ever underestimate the running time. You'd rather be over-prepared, right, for the outcome. All right, asymptotic analysis. Okay, quickly. I believe one more slide, and then we can take a very short break, and then we can go into some a little bit heavier math about big O definition. Okay, let's go over. I think I got some exercise to do before the break. Asymptotic analysis. So whenever you talk about asymptotics, it simply means we are analyzing the behavior of the running time about the input size growing towards infinity, right? Towards the limits. And running time. So that means the input size, when we do the analysis, they don't have any bound. I know physical memory always have a bound, but for our analysis, there's no bound. Mathematical analysis. All right, so let's say here, okay, so this one here, I can just go over a slide. I do have another 2 examples on the iPad. So let's say we got n here and also n squared over here. If you go back to that particular diagram over there, all right, so if you got, for example, quadratic, right? Basically, you will get something like that. You might just get n here and also n squared over here. The n squared is higher power is going to grow much faster in terms of the running time than n. So if you got algorithm between n and n squared, you should really say n should be more efficient, right? It grows a little bit slower. All right, that's what this point here really means. And then we're going to now try to talk about relative performance. Okay, we're going to estimate or approximate the running time, apply what we learned earlier, and then we're going to make some decision quickly, okay, before we get something very formal. Okay, let's do 2 examples, and then we'll take a short break. Oh, sorry, not here. Sorry, do I have that example there? Okay, sorry guys, if you can just let me interrupt. I somehow didn't have this. Okay, give me 1 moment, okay? And you don't need to see the magic I'm doing, okay? Give me 20 seconds. Sorry about that. Okay, sure. Almost there. Okay, 20 more seconds and then I will be ready. Yep, okay, ready. I do apologize for the delay. Okay, yeah, sounds a little bit ugly, right? Somehow I forgot to copy the page to today's class. All right, let's talk about these 2 exercises. Okay, so these 2. So we want to estimate the running time. Okay, so now let's talk about 2 examples over here. Okay, example number 1. Let's say we got 2 running times over here. Running time number 1, running time number 2. And we're given these 2 equations. We want to select which algorithm will be more efficient time-wise. Of course, you're going to choose the one that's going to grow slower, right? We're going to see which one to choose. And we're going to approximate each one of them, right? I'm going to do it directly to show you the process. For running time number 1, you can see that the highest power is actually n squared, right? Right away here. Compare with to power 1 to power 0, right? And once you have identified that, you can drop the multiplicative constant for that and also drop all the lower terms. So this can be approximated as n squared. And similarly, this will be the highest term and drop the multiplicative constant and drop the lower term. So that will be also n squared. So asymptotically, these 2 algorithms will be considered as equally efficient. Right? So that's the conclusion. Equally efficient asymptotically. And the context here about asymptotically is very important. Otherwise, dropping the lower term wouldn't make sense. All right? And we'll do something very similar for example number 2. Okay? And over here, the highest term over here will be, let's say, n to the power 3, right? That's also straightforward. And there's no multiplicative constant for us to drop. It's simply just 1. But drop the lower term. That can be approximated as n cubed. Also, for this one here, second one, this will be the highest term. Drop the multiplicative constant, drop the lower term, and we get n squared. So now we see which one we should really choose, right? We should choose the one that's going to grow more slowly in terms of the input size getting larger. So that should be the one to choose. Okay. So here the conclusion should be running time number 2, this guy here, should be the winner. Should be more efficient taking less time. Asymptotically. All right. Yeah, so these 2 exercises just reaffirm the strategy that we spoke about earlier. All right, any question about this? We're good? All right, so we still got some time for today. So I would suggest, why don't we take a 2 minutes break only? So no attendance take today. All right, so I'm going to pause now, and then we're just going to take a break. All right, so before the break, we talked about how you can approximate the running time function, but let's now get more formal, okay? Big O. Right? So you guys kind of learned about big O back in 1019, but I think it doesn't hurt to really brush up a bit, right? You maybe took it quite a while ago. We're going to need big O very badly for this course. Okay, so this is what we said before the break. And for asymptotic bounds, so there are 3 different cases, either upper bound, lower bound, or tight bound. For this course, we are going to mainly focus on big O. We're going to talk about its formal definition and some examples, right? And we're going to do some example today, and we'll do more example maybe on Thursday. But today, let's just get through the definition first. And for lower bound omega and also tight bound theta, it might be something you'll learn more deeply in 3101, okay? The algorithm course. All right, so let's now talk about asymptotic upper bound, big O. And for this one here, the formal definition is pretty brief, but I just want to clarify just about some common confusion, because when you see the definition there, they will mention about 3 different functions. They will mention about f of n, g of n, and also c times g of n, 3 functions there. You should really understand very precisely how these 3 functions are there to help you understand the bounds, the upper bound idea. So that's something I want to spend more time on. We've got about 25 minutes. We'll see how much we can get through. So you will see, let's start with f of n and also g of n. So these are 2 functions there. And then let's now talk about them right away, okay? Let me just switch to iPad here. So we basically got 2 functions. We got f of n. So think about it's like a runtime function. This is the actual function that you somehow derive from your algorithm already, right? It's a mathematical function. 7n minus 2, maybe 7n plus n log n, things like that. Okay, runtime function. And that one there is going to map from some input size n into something, right? Input and output basically, right? The function will take one input and return some output. And what we got is, we got input size, which is an integer, and it's going to return some relative running time. You know, for example, you got f of n equals 7n minus 2. So it will take some input and that returns an output. F of n. That's one thing you have to know. Okay, f of n. That's usually when you see f of n, that's the candidate function to argue something about. There's another function there, g. And this is what we call the reference function. Reference function in the sense that you somehow want to draw some connection from f of n to g of n, somehow. Okay? So the reference function here alone is not very useful. Somehow you will expect some manipulation to be done to g of n, somehow. So further manipulation. On g of n expected. Specifically, the manipulation we are talking about is more like changing the slope of g of n. Right? So if you guys took any basic linear algebra, whenever you say some function there, if you say c times, you're basically modifying the slope. Right? That's something we'll see visually as well. So you're given g of n, and you do some manipulation. The way to do it is by choosing some constant c, and then multiply that to g of n, right? So this is g of n, the reference function, and this is the manipulated version of g of n. So this is something you can draw some connection to f of n, actually, right? So we really got 1 here, 2 here, and 3 here. So these are the 3 things that we have to. Hey guys, it's really distracting to me, all right? I appreciate if you don't do that. Thank you. Okay, so we got 3 things over here. We got 1 here, we got 2 here, and also we got 3 here. Okay, 3 things. But I'm gonna visualize that to you in just one moment. So what's really the goal? The goal is we want to do some proof. We want to prove that the runtime function f of n is what we call big O of g of n. That's our goal. So typically, what you'll be given as test question, for example, you might be just given f of n, and then part 1, what big O family does it belong to? And then prove it. So there will be some process you have to follow to prove it. But we'll talk about the proof more a little bit today and more on Thursday. And what does this phrase really mean? Okay, so whenever you talk about big O here, so you will see on the slides, it's really talking about a family of functions, right? So this is a very important concept for you. So when you back in 1019, you learned about sets and membership, right? That's something you want to visualize for yourself, right? Okay, let's now visualize that right away. So here we got this guy over here. You can think about this like the family we're talking about. So this one here represents the big O of g of n. So this will be the family of functions that can be constructed by g of n with some certain manipulation, which we'll see. Okay? And the manipulation, as I said, just about modifying the slope. And we are really trying to show that f of n is just a member in there. All right, so now we want to somehow understand exactly what we really mean by saying that f of n is a member of this particular family. Okay, let me write it down, okay, and then we'll see the formal definition. So f of n being a member in the family means that it can somehow be upper bounded. Oh, sorry, let me just change that a little bit just to have more space. By g of n. First of all, if you remember, f of n is the runtime function, and the g of n is a reference function. And when I say somehow, that would be some proof strategy we have to follow. Okay, we'll get there, somehow. Okay, how exactly? We're going to see that when we get over the definition. And also upper bounded. So this will be some inequality you also need to identify whenever you want to do some proof. Okay. Yeah, this page here, nothing very formal. I just want to make sure you kind of see the intuition before we see the formal definition. Okay, any question about this here? Good. All right, so let's now move on with the formal definition. Okay. So the formal definition itself goes like this. Okay, like that. What we want to show is f of n, the runtime function, is a member of the family. In order to show that, you need 2 things to really show the proof, right? Let me go over them. Okay. And then we see some diagram as well. And we do some small example today. Okay. So what I want to show is f of m, the runtime function. It is a member of the family. That's exactly the diagram I'm showing. F of m is a member of the family here, right? And then there are two things we want to show, 1 and 2. You want to show some constant c to somehow change the slope of the reference function g of n. And also you want to show some n0 over here. This will be the starting point of the upper bound effects. Okay, we're going to see exactly. Okay, let me just go over that, make some annotation, and then we're going to go over this diagram here. It's going to show precisely what I really meant. So for c here, this one here is going to be the multiplicative constants. Multiplicative constant apply to the reference function g of n to change its slope. Change its slope. And you can see that exactly over here. Right? You can see the c here is really the c over here. And c is being applied to the g of n. Right? That's why you see the formal definition. That's a part 1. And part number 2, you want to choose another constant, n0 over here, and that value is going to be the starting point of the so-called upper bound effects. Okay? Upper bound in this following sense. F of n, the runtime, should be upper bounded by, should be less than or equal to. That's really what upper bounded really means. Should be upper bounded by not just g of n in isolation. It should be the modified version of g of n. Right? So this one here will be the starting point. The starting point of the upper bound effect. Well, that's the acronym I might use sometimes, a little bit informal. So whenever you see upper bound effects, it simply means here, UBE, upper bound effects. All right, so now let's take a look at this diagram over here. Okay, the way to understand this diagram here is, let me just draw that very quickly. N0 that we happen to choose, it can divide the graph into 2 halves, first half and second half. The first half over here, the upper bound effects doesn't really occur. We'll see. And on the second half over here, starting from M0, the upper bound effects start to occur. That's something we're going to see. All right. So let's now go over to the left, the case number 1. So think about, I'm trying to draw the boundary strictly less than n0. So I'm not touching m0. Okay, just over here. So we are saying that when the n is strictly less than n0. So what do we have? Let's see that very quickly, right? So just to help you a little bit, the green one I'm going to talk about is the f of n, the green one. That's the running time. And the modified version of Gn is over here. Right? You can see that's a modified version. Okay? So now you can see apparently up to around this point over around this kind of range over here, the f of n is not less than or equal to the modified version of g of n, right? Apparently it's the opposite. So what we should really see is when this is the case, then f of n is actually larger than c times g of n. Again, you want to see this. F of n over here is strictly larger than c times g of n in this case, right? Up to this point. So this one tells you the upper bound effect is not there yet. The upper bound effects not there yet. And this will be the upper bound effects you want to focus on, right? However, if you look at the second region, which will be starting from n0 all the way to infinity, right? You can see the trend over there. All right, let's now highlight that one there. Let's see this. So we starting from here and go all the way here, and also go all the way here, right? Basically, around that. So you can see in this area, so you can see this one here is a C of G of n. That one properly upper bounds. You can see the C of G of n is larger than or equal to f of n, exactly underneath. That's totally upper bounding it. So that's good. That's what we want to achieve. So here, starting from n equals n0. We got exactly f of n over here. Sorry, f of n here. Let me draw better. F of n here should be less than or equal to this one here. That's exactly the upper bound effects. F of n less than or equal to c times g of n. And that's really the upper bound effects. Is there. One thing very important for you to note. It is very important for you to choose the n0 such that it will be the earliest point for the upper bound effect to start happening. Before that, it's simply not there. From there and onwards, the upper bound effect will be there. So that's really how you should really just brush up yourself about the formal definition. All right, any question about this one here? All right, look at the formal definition, also look at the visual, and then that will definitely help. So I just want to do, got about 10 minutes. One example and a little bit proof, partial proof. Okay. So the example I want to do would be just before that. So there are different ways to say about the big O of n. You can either say f of n is a member of the big O of g of n. That's what I personally prefer. Because that one there really talks about the membership, right? Because big O of n is really a family, like a set. Sometimes people also say f of n is simply is big O of g of n. But if you really think about the set idea, it's not really accurate. How can you say a member is a set? Doesn't make sense. But you can say that, that's okay. That's what people say anyway, right? And, or you can say f of n is order of g of n. That's also fine. Okay, choose the one you like, right? Doesn't matter. All right, let's now do one quick example together. Let's say the runtime function we have is a times n plus 5. And if you apply some approximation principle, we can just choose the highest power here, just n. So we can easily guess it should be big O of n, upper bound. All right? But if you want to prove it, you cannot just say, oh, I just dropped the multiplicative constant and dropped the lower term. It's not enough. It's a formal proof. So the proof over here, that's something you guys can review before Thursday to get more comfortable. But basically, this paragraph just tells you, in order to do that, according to the definition, you got to choose the C and also n0. All right? That's what you got to do. And I'm going to help you a little bit, okay, over here. Let's say here, if I got my runtime function 8n plus 5 over here, and somehow I claim that it should be big O of g of n. So g of n here is a reference function, right? So now I need to choose some c, I need to choose some m0, okay, for now, okay? Let's say I choose c to be 9, simply because since the multiplicative constant is here is a, I'll just choose one larger, just choose 9. So it's guaranteed to have a bigger slope, right? Let's say I choose that. If I choose 9 over here, the question will be, what exactly will be the n0 starting from which we're going to get upper bound effects? That's really the question. Before we even answer that, let me ask you guys here to help you a bit. So we talk about what about n0, right? And given that we already chose 9 to be this c to be 9. The question here would be, can n0 be 1? Remember, according to the formal definition, n0 can be larger than or equal to 1. I'm just choosing the minimum. All right? All right, so this will be a little test about your understanding so far. Right? So now, given that I already chose c to be 9, can I choose n0 to be 1? Aha, How come? Yeah?
Because if you choose n0 to be 1, then g of n will not be bigger than.
Bigger than. Upper bound effect is not there. Exactly. Okay, guys, I'm going to write it down. Your fellow student was exactly right. Okay, the upper bound effect is simply not there. So if you apply that, so this will be a very important exercise for you to do, because anytime you want to somehow do some counter example, you have to apply the numbers in there. We'll see more on Thursday, but just for this one. If I try f of n over here, I simply plug in 1, right? Because I say, can I try 1 here? F of 1, is it less than or equal to? And g of n is n. And then I chose c to be 9. I'm asking this. If that's true, I'm good. If that's false, no. Well, obviously, you can see that f of 1 over here will be 1 times 8 plus 5, which will be 13. Is 13 less than or equal to 9? No. So upper bound effect is not there. Okay? So false. Upper bound effect not there. Okay, hopefully you're okay with this. Very important to see how to show when the upper bound effect is not there. It's equally important to show otherwise. The follow-up question for you will be, what would be n0 then? What would be the smallest number for n0 that we're going to see upper bound effects? 5? Okay, that's pretty good. Okay, you guys are so great. You know, also in the morning class as well. It's like instantaneous. You tell me the answer. That's great. All right, so go to the slides. Okay, I got some table here for you. Basically, that's something you will gotta try, just in case you want to find it out. What I tried together with you was about n is equal to 1. Right? You can see 13 is not less than or equal to 9. You try 2, also not true. You can see 21 is not less than or equal to 18, and etc. So 5 here will be the starting point where you got 45 less than or equal to 45. However, I would suggest you try one more just to see if the trend is going to continue. Normally it would, because the function should be continuous. All right, good. We also got 53 less than or equal to 54, right? Which is good. All right, important technique for you to have when you have no other clue about a function, about what to choose. However, what I'm going to show to you partially, I got about 4 minutes. I'll see how much I can cover. There is a proven strategy for us to really choose the C and N0 in a system, in a way that's been proved. Okay? So I want to show you the strategy first and also show you some proof. Because the proof itself can also give you some insight into the formal definition. So we'll do both. So according to the strategy, we can simply choose C to be 13 and N0 to be 1. It'll be up to you as an exercise to double check that when I choose this one here, the upper bound effect is going to happen right away. Okay, you guys can try. Very easy. Just do what I try to do on the page. So let me now go over the strategy with you, which will be on this particular slide. Okay. Okay, I'll get to this example maybe on Thursday, but let me talk about the strategy. Okay, I got about 4 minutes. See how much we can go. Let's say if I have some runtime function here, f of n, and it's a polynomial, and the highest power is d. Okay, so I'm trying to arrange that in a sorted manner. So here I say n to the power 0 to the power of 1 all the way to the power of d, right? In an increasing order for the power. And the multiplicative constant is like a0, a1 all the way to ad. Okay, let's say if you can arrange your function in such a fashion. Not surprisingly, it should be a big O of the highest power, right? However, how do you prove it? In order to prove it, according to formal definition, you got to choose the C and N0. So the strategy that always works, almost always works, let me say, almost always works. N0 can just be 1. But for the C here, it's going to be the summation of the absolute value for all the multiplicative constant. So what do I mean? If you look at this term over here, a0, a1, up to ad. So these are the multiplicative constant. They may be positive or negative. You have to make sure you take the absolute value for each one of them and add them up together and get the answer. All right? That's the strategy. All right? So what I want to do is to take 3 minutes just to try to prove it. Okay? And then we'll apply that as well on Thursday. Okay? Okay, let's see how far we can go. In order to prove this strategy here, okay, just very simple math, but you can really get some insight from there. Okay? So in order to prove it, basically we want to take a look at C and N0, and we want to make sure the upper bound effects is going to start from 1. And then it's also going to extend onwards. These are the two things we're going to see. So we're going to see a little bit here today. Okay? So over here, we're going to show two things. So number one, so remember the upper bound effects is such that we got f of n should be less than or equal to c times the g of n, right? Just remind yourself, that's the upper bound effects. Okay, we're going to apply that for both cases. Now, what about case number 1? Case number 1 is when the input size is actually 1. So f of 1 versus f of n. So we're going to get f of 1 less than or equal to, and the c, I'll simply put c here, but it can be expanded into this value over here later. And then c times, and then we're going to get the g, because you can think about this reference function here is g, the g of n, n to the power of d. But now in our case, because n is 1, so this one here is also 1. That's what we want to prove. Okay, number 1. And let me say the number 2, and then we are done for today. And number 2, we also want to make sure the upper bound effect extends beyond. So f of n in general less than or equal to c times n to the power of d. And here we say n should be strictly larger than 1. So we are considering both the 1 case and also larger than 1 case. Right? So we're going to prove these two. They are rather easy to prove, but it can definitely give us some insight. All right, thank you. I'll see you on Thursday. We'll continue from there.